All right, so this is the June 13th iteration of the Resource Management Work Group. So today on the agenda, we have about 4 topics. I think get an update from Avesh and Vikas on the resource class proof of concept that was done here at Red Hat after our face-to-face. And then time permitting, we'll get through the huge pages update, device plugin proposal, and some updates on CPU manager work that's been going on across the community. So with that, Vesh and Vikas, do you want to kick things off?
Yep, I can. We can have the demo. I have recorded it. So shall I share my screen and start it?
Yeah, go ahead.
Thank you.
So just some backdrop on this work while Vikas is getting that up. Basically, out of the resource management work group, we tried to come back here at Red Hat and figure out which things we could try to accelerate via proof of concept before doing a full design. So I think we had said after the work group meeting that someone needed to prototype this to make sure the scheduler could make good decisions. So I think Vikas has kindly gone and prototyped that and is going to give his experience. Go ahead, Vikas.
Okay, thank you. So here I have we have in this demo we have 2 nodes.
Yeah, because we cannot see your screen, it's too small.
Could you make the text size in the terminal bigger?
1 second.
Either that or resize the terminal window better. That's better.
Yeah,
great.
That works.
So we have 2 resources here, two nodes here, and I have had for now on each of these 2 nodes, like one node has this fake device NVIDIA GPU, which has some extra memory, 50 GB, and this initial. So let me restart. So we have 2 nodes, the 620 and 730. On the 621, we have this NVIDIA GPU device with less memory. And on 730 node, we have one more device which has a bit higher memory. Both are of type NVIDIA GPU. And now we will try to create 2 resource classes. One requesting just the type as NVIDIA GPU, and another will be requesting devices which another class will request the devices which will need some NVIDIA GPU resources with higher memory, which can be satisfied only by the resources devices which are present on the 730 node, which other node. So this is our first resource class. This resource class is querying only the NVIDIA GPU type resource. And now that we have created this class, scheduler will figure out and from the nodes like what all devices can satisfy this resource class. And in the status of this resource class, it will update the status of this resource class with the available devices. So because it is just NVIDIA GPU, so it has 16 as the allocatable from both the nodes, 8 of each type of devices. And this is another resource class. In this resource class, we are querying the same type of device, but with a memory higher than 30 GB. And this can be satisfied only by the devices which are on this another node, 730, not the first one. So let's see if the scheduler has computed this thing correctly. And yes, allocatable is 8 for this resource class, which scheduler has updated in the status of this resource class. And now we are going to create some ports to test if the scheduler is able to correctly translate the resource classes into these devices. So Now, first let's launch a pod which will request 4 units of this high memory resource class, which has just 8 allocatable. So this should be satisfied only from the node, this second node, 730 node. So let's see if the scheduler has done its work correctly. So scheduler has correctly figured out the device for this resource class and cached the device selection as annotation in the pod. And let's verify the node also. So node is also correct, 731 for this pod. So now out of 8 devices, 4 are gone. Let's see if the status of the resource classes are correctly updated. Yes, so for this high memory resource class, request is 4. It has got updated correctly. And now also another resource class which requests for the type NVIDIA GPU only. This request should get reflected there also, because devices from both the nodes were satisfying this resource class, which was asking only for type of device NVIDIA GPU and not any specific constraint like memory. So though we launched a high memory pod, but that request got reflected in this resource class as well. Now let's try to create a pod with 8 units of this high memory, and this should fail on the predicate because we have only 4 left on this another node. So we tried to create 8 this pod which is requesting of this resource class NVIDIA high memory, 8 resources, and it should fail. It should not be able to launch. And here it's saying that insufficient NVIDIA high mem, it has got failed. Now, if we try to launch a pod, which is requesting just NVIDIA GPU, not the high memory of 8 units, it should get launched on the first node, which has NVIDIA GPU devices with less memory. So let's try to launch this pod, which is requesting this first simple request, resource class request of 8 units. So this got launched and it got this correct device also, and let's verify node of this pod also. And that's the first one, that's also correct. So now let's see how the accounting has happened for the resource classes after this allocation. So here if you see, this has got reflected here also. Earlier it was 4 and now 8 has been allocated. So request of this resource class has become 12 and this is still 4. Which is high memory resource, NVIDIA high memory resource class. Now let's try to launch another pod with similar request as the last one. It should fail. Like now we will try to launch again the same pod with asking the normal NVIDIA GPU, but with 8. But it should fail because there are only 4 devices left which are on the second node. So let's verify it should fail. With the proper message, event message. Yes, it has failed because 8 are not available at all. We have only 4 left on the second node. So let's try to now. So it has failed. Let's try to get 4 units of this resource class and not 8. And this time, let's try to launch this pod which is asking for, and this has got launched. And now let's see accounting of resource classes, the requested of both resource classes should be equal to allocatable. Now, because we have consumed all the devices, so for this the first two resource class, which is asking just NVIDIA GPU, so request is equals to allocatable. And for the second class also, which is high mem. So both have reached their maximum. And let's try to see the, okay, all these ports we launched. So these failed on the predicates, and these ports consume the total resource devices. And now let's see if on delete, it releases back all the devices and resource classes gets updated correctly. So let's delete all the ports. And it should get reflected in the status also. It might take a while. Okay, it's gone. So again, back requested is 0 and allocatable is 16, which is constant. And for other resource class also, it has got requested 0 because we have deleted all the ports. That's all I have got working for now. So, and I'm working to test and cover other complex scenarios such as grouped devices, grouped resources, and overlapping resource classes within the same port request. And I have prepared I have come up with a draft of design doc as well. And that's pretty much all from my side for now.
Another question. So when we specify these like in the pod spec or like the request, how do we define those words?
Define what?
So like NVIDIA high mem, or tomorrow we want to have like ATI, I don't know, low mem, various types of
Devices.
Types of other devices that we may have, network, or I don't know.
Right.
So how do we define those?
So there is already one proposal, a PR there from one NVIDIA guy. So the idea is that every vendor, device vendor, should come up with their plugins to auto-discover their devices, okay. And they should create this kubelet will. After connection gets established between the kubelet and the device plugin, it's the device plugin's responsibility to discover the devices available on the node and get created all these devices on the API server, these objects for the devices.
And yeah, to an extent.
I'm having trouble hearing you, Vish.
Yeah, can you speak up a bit?
Yeah, sure. So I was telling Bobby that name standardization is going to happen through vendors. Mm-hmm. Like they're going to standardize on some names, but that's not going to be enough in that like the resource classes are essentially fancy labels. There will be like depending on your deployment, you might want to have restrictions on what is available, or you might just open it up for all users, right? Like if you're having a research deployment, at which point you want to use like different combinations and see which ones work best for you or your set of workloads, right. You might just open it up. So what resource class names get exposed is going to be per deployment.
Yeah, so we are going to, so I see like a couple of issues. One is that we are going to lose conflict compatibility among clusters.
If like deployments end up exposing resource class names that are not typically exported by like off the shelf hardware plugins.
Yeah, sort of. And also, it's not only that case. Imagine this. So we have NVIDIA high mem today, and then we have all the cluster set up and everything. So a year later, NVIDIA comes up with a new version of the hardware. And probably if someone at the cluster level wants to distinguish between a cluster that has the older version of the hardware versus the new version of the hardware, they have to come up with a different naming again about.
I'm sorry, here I want to comment. Actually, we have predicates. So if NVIDIA comes up with new version with the help of key value and the operator, that can also be satisfied, I think.
So that, or you end up just being kind of like cloud VM sizes, right? Where you have like M4X large, M4X large, higher number.
Some sort. We probably need to come up with some sort of a standardization.
And one more thing, because here we are mapping resource classes to devices, and if we update the devices, that existing resource class would anyway map to the new device, right?
Yes, but sure, that could happen. But my point is that if the user, for example, wants to say, hey, I want to have that older version of the hardware or the newer version of the hardware with like high memory, how can the user specify this?
So user will mention that particular key value pair and operator in the resource class, and then resource class will match with those devices.
Yeah.
Does that make sense?
This question is slightly different in that the naming scheme that we use should make sense. It cannot be like some like arbitrary foobar which does not express what that underlying resource is.
Yeah.
Like Derek was saying,
So sorry to interrupt you, Vish, but when I was building the device proposal, that was one of the questions I was actually asking myself. And one of the solution, or at least somewhat solution that I came to was that you should actually describe the type of hardware or the kind of memory in properties, so in a map. And the name should only reflect the name should reflect some kind of unique ID, and you should actually be able to select with the kind. So for example, you would say GPU, and then in your property, you would say, well, the hardware is Volta, or the hardware is Kepler, or the generation is Kepler, the generation is Pascal. So I think we still have this this problem where if a vendor chooses to change the property name, then it becomes a problem. But it somewhat differs the naming problem to the property, and not just, you wouldn't say high memory, NVIDIA.high memory. You would just say, I want an NVIDIA, and then with property hardware or memory equals 8 gig.
Exactly.
Like we're sort of rabbit holing on this issue, given that we have 3 more agenda items. An important thing that we need to discuss. So should we just wait for Vikas to post a proposal and then discuss that?
Yeah, sure. Yeah, I just wanted to say one thing quick. I kind of liked what Donat said, but at the same time, the user should probably be able to omit all the details if they want. For example, a user may not care at all about the version or whatever, and say, I just want to have the GPU, whatever GPU is available is fine. That should be possible as well. So basically, we should address both sides.
Right.
Yeah. So just to level set, I mean, one of the things I was hoping Vikas could maybe spend a minute or two on was talking about the things he had to add when doing this prototype that we didn't yet previously capture. So the thing that stood out to me, Vish, in contrast to what we originally had written up, was that he added a status section to resource class. And I wasn't really quite sure, Vikas, if you can pick on like why you felt that was necessary versus just the scheduler holding that status locally in its cache.
Just because the user can have a view like which resource classes I can and what quantity I can request in a pod. Otherwise, if only scheduler knows like how much units of each that particular resource class is remaining, user may request that and it may fail. So just for the user's sake of so that he knows how much is left, which he can query request in the pod.
Okay, so the scheduler is not necessarily using that to make the scheduling decision. It's still looking at the node to individual count that it captured. Because I guess what I was wondering is like if I couple this with a cluster autoscaler, like I would expect that number would go up and down all the time. So I wasn't quite sure how critical the status section of resource class was for driving the actual system behavior versus what the scheduler holds locally.
Derek, if I understand your question correctly, so you're saying if the new nodes are coming and going, So yeah, because in the current implementation, whenever the new node is added, based on the what devices it has, resource classes are updated.
Okay, so I guess in the interest of letting folks go to the next schedule, I think just to level set people here, I think we said something like resource classes were needed to support heterogeneous device deployments. So when we go back to our roadmap, I don't know if we end up saying that this needs to be here before or after GPU support moves up. I think that's up for debate, but I think in the long run, this is a potentially an approach that at least we can know we were able to prototype to know that we could differentiate devices in this way and it was achievable. So I want to thank Ikas and Avesh for putting this demo together. And if there's no other comments, we can move on to topic 2.
One thing, since you raised it, it's that like resource classes are essential if you want to have any more advanced scheduling. If you're okay with like having primitive scheduling where you just get like one among n devices and you can't like filter among those n devices, then like just the existing primitives should be good enough. So it's up to us when we decide that these additional scheduling primitives are a necessity. So I'll try to start a discussion around that later this week as to where resource classes should fit in our roadmap.
Awesome. All right. Well, thanks again, Avesh and Vikas. And let's see, topic 2 was huge pages update. I'm okay, Piotr, if you want to lead the discussion, or I can help out as well.
Yeah, so hi, I'm Peter from Intel. So maybe let me share my screen. So Derek previously presented the proposal how to integrate huge pages as a first-class citizen in the Kubernetes. But essentially, there are 2 ways of using huge pages. One of them is directly via syscalls, like JVM uses it, like the transparent way. And another way is use it as a huge TLBFS. So this is the case, like for example, DPDK application is using that in that way. So I am proposing another approach. So basically creating a new volume plugin huge pages. So it basically creates a huge TLBFS mount and mount it directly into the pod sandbox. And phase 2 would be implementing the admission controller. I know the name is maybe not very cool, but yeah, you can change it. And translates the volume mounts into the huge pages first-class citizens. Like for example, these or the resource classes like later. So this is a document, it's available in the agenda, and I can show you the demo because I have a POC ready. So if you want me to change to my terminal, okay, it would be this. So can you see my terminal?
Yep, looks great.
Yep. So basically on this machine, I have 100 huge pages available. I will create a volume. I will create a pod which requests 200 megabytes of huge pages, and the huge page size is 2 megabytes. So if I create this pod, we can see, let me mount. Typo. We can see that volume mount was created with type huge TLBFS and the options specified in the pod spec. And if we see prods mem info once again, we can see that 11 pages is reserved because application that I am running is basically just reserving huge pages. And I have another POC ready because I think we can easily parallelize 2 efforts. First one would be to implement only a volume plugin, and the second step would be the admission controller when huge pages lands in the Kubernetes. And second approach is with the with the admission controller, it's basically the same pod, but if we do get pod Ubuntu, we can see that the volume mount was translated into the resource request huge pages. And you can turn on and off the admission controller by just specifying its name, huge pages volume resource. So that's basically the update. Do you have any questions?
Yes. Why are volumes being combined with the rest of the resource pipeline?
Because when we only use the huge pages volume plugin, we have no accounting, and the huge pages are finite resource.
If it depends on what huge pages are, right? Like if huge pages are a kind of resource where you can have like multiple shapes, and then you want like more advanced scheduling primitives, what resource classes we're trying to tackle, then pulling in the volumes abstraction is going to complicate everything. Right? Volumes abstraction is great because like you're giving huge TLBFS, and like so it's a file system thing, and like volume sort of naturally maps there. So if you're going that way, then I would prefer going through the volume pipeline because it has quite a bit of scheduling primitives already in there. I don't know, it doesn't feel good to
okay, but there are two.
We need to cover accounting in both places, right? Like I kind of view the huge pages back volume as similar to like a temp-fs back volume, and
yeah,
your usage of temp-fs will be limited by your overall memory limit anyway. And I feel like huge pages should be similar.
Sure, but the point is that so that's an accounting problem at the node, right? It's not an accounting problem in the cluster. For example, if you request 500 megs of temp-fs, we do not increase a pod's memory request.
That's correct. So I don't know if that necessarily was stated as a requirement, like that would. I guess my concern is as long as it's accounted for on the node, I'm okay. Whether or not we decide to express the sum of the huge page volume sizes into the huge page memory request, like, or if instead we say your huge page memory request needs to already be greater than the size of your volumes because, and have it work like memory, then that's fine for me as well.
And what's the point, Derek? Like, is the goal to ensure that like user X does not consume more memory than what they are expected to? Is it like a quota problem, or is it like an isolation problem?
It's both.
So from an isolation standpoint, huge pages are already statically sized. So, so you get isolation anyways, right? And from a quota standpoint, if you're using volumes abstraction.
Well, before you jump too far, so huge pages are statically sized. That's correct. But one of the suppositions I was making was that huge pages can't be consumed by best effort style pod, right? You must make an explicit request to use huge pages, like,
right.
And so you need to at least say on your pod spec the aggregate amount of huge pages you expect to consume, whether by volume or non-volume usage patterns.
Just to like that's again an admission problem, right? In that like you do not want best effort pods to consume huge page volumes. Isn't that an admission problem?
Well, I don't want pods that request to use huge page volumes to land on nodes that don't even have huge pages advertised.
Right, but that's again a scheduling problem. Right? Like we have the same problem with like local PBs. Right? Like we're dealing with the exact same problem in that like once we go with local PBs, then like they're similar to huge pages, right? In that they are node local. Their cardinality is 1, which is single node.
But their cardinality isn't 1. What do you mean the cardinality is 1?
Well, I mean, if strictly local volumes that are like, for example, rotational media that are attached to a single node, its cardinality is just 1, right?
Yeah, but I can have multiple pods on a same node use huge page back volumes.
Yeah, that's okay. And there can be multiple local volumes that, and there can be multiple pods. So it's many-to-many mapping. So there's also like sharding involved in that. So that's a slightly more complex use case. So I feel like we either can follow that same pattern where node advertisers want like huge page local volumes exist, and like use the same scheduling stack to schedule huge page volumes for pods, or we just go through the other road of like not taking volumes, or not abstracting huge pages as volumes, and then abstract them as like just regular resources and have kubelet do what is necessary for that.
So I think you need to do both. I don't know if we need to rat hole on it too much here, but I guess I do not really want to have to pre-allocate huge page volumes of particular sizes. And I feel like that's kind of what you're suggesting here versus what Peter's demo was showing was he was dynamically creating the volume. Am I correct?
But that's going to change the quantity, right? Like that's like, I don't think our system has been designed for that, right? Because if you're dynamically allocating huge pages, then your capacity.
You're not dynamically allocating new huge pages. He had an existing reservation, or he had an existing amount of pre-allocated huge pages. He was just saying that the volume, or having a volume that's backed by huge pages from that already pre-allocated pool, can be created dynamically. But he's not dynamically creating new pre-allocated huge pages. He had a fixed capacity.
Yes. I have pre-allocated like huge pages beforehand. It has to be done manually by the operator, but then I create dynamically the pods that are using those. So if I will create another pod which will request the huge pages, it will just create another huge TLBFS volume and mount it directly into Sandbox.
Yeah, I mean, to me, this works like TempFS.
Well, I get that. It's just that with TempFS, we don't really have interaction between volumes. Like TempFS doesn't have isolation built in, except if we like try to limit its size. So like isolation sort of comes for free with TempFS because we reuse pods memory specification. Like, I don't want to rabbit hole here, but I still have like some strong opinions on like interactions between these two pipelines. So maybe like who is interested in that, like who is a stakeholder in this effort, then we can all like offline or discuss over a doc or something.
Yeah, that's fine. So I know both Peter and myself are going to refine the doc further on the proposal, but we can take those issues to the proposal. But generally, I think to make huge pages successful, you need to be able to consume it in both modalities.
Yeah, we can always go with a road that you can explicitly like define in the pod spec the huge pages volume mount and the request size if you want to like account it. Because I just didn't want for a user to specify it explicitly in the volume spec. So just right here, we don't specify the request, but you could do it.
Yeah, I mean, like if you go down the volumes path, we could like imagine using storage classes, for example. Right? You can say that you have a huge page storage class of like size foo, and so by default you're going to get huge pages of size 10 gigs or whatever sizes you're pre-allocated. So yeah, I don't want to like keep talking about that.
Okay. Yeah, we can work through that. I mean, I know volumes are tricky. Let's just do it as a flex volume driver too while we're at it.
I tried it. It can be done.
Okay. Yeah, I'm just joking on that one. All right. Well, thanks for the update on that, Peter.
Thanks.
Let's see. We have 25 minutes and 2 topics. Just out of curiosity, is either one of these relatively quick? And then we could do that one first and then end on the last one, or?
Well, so I just want some feedback on the proposal and what people think are objectives and non-objectives in my case.
Okay.
Can you do it as a PR review, or like would you prefer going over your PR?
I think it's more interesting to, because it seems like a lot of people want to go in different directions. I think I was mostly thinking of, in your case, driver installation. And I think there was another part, but what I'm more wondering is that, is my PR sufficiently, is the scope of the PR sufficient for everyone? And can I move forward with this Or should we build something more on top of with it?
I think the first step is to figure out a solid requirements for that's what I would recommend. Make sure that the requirements are agreed upon by the community in general before you spend time implementing it. So I still feel like the requirements are not fully solidified in your proposal. So should you just take this week to attempt to finalize the requirements? Because I don't think everyone has gotten a chance to actually review it, given that 1.7 was happening.
I understand, yeah. So do we delay this subject to the next meeting and try and have people review it a bit more?
Yeah, that might be helpful. Okay. Unless you have very specific questions that you want to discuss.
Well, in my case, I was just making sure that everyone agreed on the objectives. But if you're saying that not everyone here did have time to review it, then I think my question should be delayed to the next meeting. That seems reasonable.
Okay.
And I do agree with Vish. I mean, and also kind of we have to think a little beyond just GPUs. Try to make it as generic as possible, NICs or other use cases. So I think definitely we need to do some thinking. I'm actually.
Juan, can you speak up?
Sorry. This is Ramki. So what I meant was we need to think a little beyond just GPUs. Try to make it as generic as possible to other type of devices such as advanced NICs. I'm actually looking into that this week. So I'm actually looking.
I agree on that. I agree that's why I want some feedback on this. And I'd be really interested in what you think on the PR would make it more generic.
Yeah. Renaud, just to give you some form of realistic expectation, I think this general proposal and the work that you're doing is going to be really critical for the project in general. Mm-hmm. It's going to lay the foundation for many new features that we want to implement. So it might take some time to finalize your.
Oh, I agree.
Get frustrated in that process.
I'm not even sure that it might make it in 1.8. So that's. I understand that it is going to take some time, and realistically speaking, there are going to be a lot of people trying to go in different directions.
Yeah.
Okay, well, I think this subject is finished in that case. Thanks.
Okay, well, thanks for now. I know I didn't get a chance to read your proposal in depth, so I will try to do the same. Given that, I guess the last item on the agenda, Seth, Connor, Nicholas, do you guys want to give an update on how things are going with the CPU prototypes?
Sure. So we have I've got a prototype of the static CPU manager, which is the one that there's no feedback mechanism. It just looks at if a pod is guaranteed and the container makes an integral CPU request, that rather than using CFS quota and spreading that one CPU request across all the cores, it will try to create a shared pool where burstable and best effort pods run, and then give that, and then basically through CPU sets, push the burstable and best effort pods off of a core so that this guaranteed container can run on a core less interrupted. So is there anything that you wanted to say at the beginning, Connor, before I do the demo?
No, let's jump in.
Okay. Okay, can you see?
Yeah, looks good.
Yes.
Okay. So what I have here, I've got just local cluster up running on this other tab, and it came up with kubedns, and I'm actually going to use that here. So in my proof of concept, I've reserved core 0 kind of as a cube or system reserved element. Just we don't have to do that, but it can be done, and it makes it easy to show right off the bat here that what the shared pool is. So I've got the kubedns running here, and if we KubeDNS is a burstable pod. So if I go down, I'm in the CPU set controller here, C group controller. So if I go down into pods, burstable, you can see so there's 3 containers in the KubeDNS pod, and plus the pods container, that's 4. And if I
can you scroll your terminal up so people can see the top? Okay.
Yes. So you can see here that these are the CPU sets for those 4 containers, and this is the pods container, and it can run on all the CPUs, but the actual containers in the pod spec are confined to the shared pool, which is currently CPUs 1 through 3. So if I go in here and we'll look at this. So this is what we're calling a guaranteed container, which is kind of crossing the streams, since guaranteed is a quasi level concept and quasi applies to pods. But in this case, all I'm referring to is a container in a guaranteed pod that has an integral CPU request, which is what we're deciding that the static manager is going to lock onto right now. So basically, yeah, that's the limits. And so if I create this, okay, so now it's running. And if we go over here, now we're doing this watch, you can see that it's switched to only CPUs 2 and 3. That's because these burstable pods are in the shared pool and they've been shoved off of core 1, which was allocated to the guaranteed container. And it is the bottom of my screen getting cut off. Can y'all see that bottom line with the cursor?
Yeah, that's what's getting cut off for me.
Oh,
Can you see the blinking cursor at the bottom?
No, but it could be because I have this zoom toolbar on the bottom that I can't get rid of.
Okay. I'll just try to keep it at the top. So if we get, so here's this, here's the guaranteed pod. Go into that and look, here's our pods container, and here is our container that's in the pod spec confined to CPU 1. And so no other pods can run on CPU 1. Right now, the way we've got it configured, system daemons can run on any CPU. Interrupts can run on any CPU. So, I mean, this isn't a hard isolation, but it does keep other pods from running on CPU 1. And just to show that it can extend, if we create another one of these, there. And if we go back to here, you can see our second guaranteed pod here. And I'm not sure which one was which. Was it just in 4.5? 1 pod 1. You can see that it's on CPU 2. And if we go back into the KubeDNS pod, you can see that the shared pool's been shrunk to 3. So right now it actually doesn't handle the case where you exhaust the shared pool, but we could write code around that. But this, still a proof of concept. So, but that's what we're looking at doing right now. So that's the demo. Any questions?
This will ensure that the sum of requests across multiple pods would still be met, right?
Yes.
Okay. And I assume that if you have a non-integral request, just the integral part of the request would translate to exclusive cores. Like 2 pods.
Okay, so we changed that in that if you don't use an integral CPU, then then you don't get it. You're not a guaranteed container. So, for example, a request of 1 will get you a core assignment like this. If you say 1.1, you're in the shared pool, and no part of your CPU request is fulfilled by a dedicated core.
Why?
Because it's a mess for CFS. Basically, to have 100% of one core and then 10% of another one, and having like an asymmetric CPU set, the scheduler goes nuts. I tried it, and it doesn't. It seems like it almost disables load balancing to some degree, especially if your workload is single threaded. It doesn't make much sense.
Yeah, I mean, if it's single threaded, then like you just need single hardware threads. But like if it's multi-threaded, and if your application is smart enough that like it's able to figure out what exclusive core it gets, and then it pins the important threads to that core, and the rest of its threads can run on any core, then is it still an issue?
How would it know which one is the important hardware thread, which is not? And
but
you
it's
will have
right. Like, so if I'm writing an application, if I'm doing garbage collection, for example, I might choose to run it on any core. Whereas if I'm having a web serving thread, then I might like pin it to my exclusive cores or my non-public cores.
that's something you'll have to find an API to expose, right? So either the exposable files or environment variables in order to tell the runtime how to go pin its stuff.
Yeah, totally. I mean, I was assuming that like download API would be taking care of this feature.
Yeah, so that's still an open topic. I think we agree that we're going to have to do download API on discovering what CPUs are in your allowed set, and then that's even more important when these things get dynamic with the other policy.
Right.
In terms of your pin set, you can always look at proc self status, and then you can see your CPU flags mask there. In terms of knowing what the exclusive core is, that's something that we could push down into an environment variable. For the static policy, you know that that won't change for your lifetime. That's the guarantee that the static policy gives. So if we somehow did some policy that would allow you to span the shared pool and an exclusive CPU, then you could just hand those masks and figure out where you want to pin your important things. But
yeah, it's really a nightmare. I wish it had delineated all the problems as I encountered them, but allowing the mixing of exclusive cores and shared cores is really doesn't work very well from a scheduler standpoint, or from so with CFS, for example. If you so what I'm doing right now, if it's a guaranteed container, I'm not setting CFS limits on it because it's implicitly confined to one core and therefore cannot use more than one core, and so I don't have to use CFS. If you're basically painting the scheduler into a corner by using CPU sets and CFS.
It's an application. It's an application owner's choice, right, Seth? And that like, if you really want CFS out of the way, then like always request integral cores. But if your application is one where it need not like get integral cores all the time, and it can, some part of the application can survive public cores or shared cores, isn't it an application problem? I mean, application authors need to know the difference in like performance guarantees. But
I can see applications that already exist today looking at proc self, like Connor is suggesting and figuring out. And if you run, if you don't allow mixing of exclusive and shared cores in a pod, then the application can assume that all of the processors it's allowed to run on, if you configured it this way, are exclusive. So you don't have to have this guessing.
One thing I'm concerned about is like, I think if we could do this on like a per application type, like I think JVMs, doesn't it just look at the actual enumerated set of lists and assume it has full access to those? Like I'm wondering some of these like common middleware platforms that people might run, how much they can slice and dice, where I don't know. I don't know if the majority of applications are as savvy as the ones that Vish is enumerating.
Yes, I don't think that those are real.
If I'm doing 1.5 on a JVM, I might actually get worse performance.
Yeah, and I mean, in my experience, I can see people assigning between 0 and 1 cores. When you do fractional cores below 1, that makes sense. Above 1 core, like, are people really going to assign 1.5 cores instead of 2? I think above 1, they kind of go integral.
I mean, at least internally, that's not
4 because all the other tuning happens on the core basis as well. Like I'm talking about interrupts, for example. Everything else operates on the unit of 1 core, except for the CFS. So because there's more than just CFS involved in actually getting these workloads running, we have to take the lowest common denominator, which will end up being 1 core or integral cores.
So all I'm saying is, like, I'm not saying that the use case of like getting rid of CFS as much as possible is not valid. I'm saying that there's also an additional use case where you might want to run part of your application on public cores. So even that aside, the other issue that has been brought up here is that of like lack of standard Linux container APIs around resources. Like we are adding new primitives and policies as part of Kubernetes, and probably like other orchestration systems will add that. And like Linux APIs in general are not like container ready. So we're going to have that problem for legacy apps. So we have to set the path for like modern Kubernetes apps that are probably being rebuilt for Kubernetes and like give them a good downward API. And then on the other hand, also figure out a transition path for legacy apps. Like Ubuntu has this whole like proc a fuse file system. So we have to like come up with some other solution for giving an API that's through procfs that apps are already consuming.
So a couple of questions here, Seth, that you can talk to a little bit. Like, why was the choice of putting the pause container on a shared core done?
That's just the limitation of the POC. It's handled in a different area of the code, the creation of the pause container. So, and I mean, the pause container is hopefully something that we don't have forever, right? I mean, it's just a kind of, hopefully it's vestigial at some point, but yes.
I guess what I'm wondering is, like, did people expect the pause? Like, is that a bad choice for people to see the pause container not on the exclusive core? Because like I thought in a multi-container application, I didn't even know which ones I'd want it to be on, to be honest. So like, I was just wondering if the shared core was a conscious choice.
It wasn't a conscious choice. It was just something that's not included in the POC. I mean, I could find out where in the code the pause container, the pause container is just created in a different place than the containers that are in the spec.
So right now, isolation is per container, right? Not per pod, at least exclusive cores.
Correct. And that was done because the runtime handles the setting of CPU sets.cpu in the C group.
Okay. So
and CPU sets.cpu isn't inherited. So like if we set it in the pod level C group, the Docker containers, they don't implicitly inherit that.
Well, is that a Docker bug?
No, that's just the way the CPU sets controller works in Linux.
But
for better or worse,
it's still going to be restricted by its parent, right?
But Docker actually sets it to the full mask unless you pass a flag.
So it's a bug in the system.
That's how I interpreted it.
Okay. Because
if we can get Mernal or someone to look at that, we should try to get that fixed, Seth. Like I would expect we should, like cryo, I think we should be able to get cryo to do the right thing. And that could just be a bug in run C that we could get, so Docker picks it up as well.
Okay. The reason I ask is that like pause is at the pod level. So I'm trying to like understand how the policy works as part of this proposal. If a pod is guaranteed, then like and if all its containers have integral core requests, is that when they will all get exclusive cores, or like, I mean, how does it work? Is it like
the decision is made on a per container basis. And so if you're in a guaranteed pod and you have an integral CPU request, then you get the exclusive cores. your peer containers inside the same pod might be in the shared pool.
Okay, so then that typically means that your pod might end up having a CPU mask that spans exclusive and public cores.
That's right. That's why we're currently not doing the confining at the pod level.
Okay. Yeah,
So
I mean, go ahead, Derek.
I'm sorry. The other question I had that I don't know is obvious, or not a question because I know the answer now, but I think it's worth talking through is, I know me, you, and Connor met to discuss like the idea that did we need to move everything off of the core before starting the pod, if it had exclusive cores, and maybe you can talk through like the rationale we made at that time and why we made it.
Right. So we made the decision that, this is the way it is in the proof of concept, that the CPU set needs to be configured before the container starts. So the CPU set is actually configured between create container and start container in CRI terms. That way, when the application comes up, it could probe procfs to figure out which CPUs it's confined to. However, that doesn't necessarily mean that at application start time, all the other pods have been knocked off your dedicated core yet. That we didn't want to make the thing synchronous, because there's potentially lots of containers on container CPU set C groups on the system that need to be updated. And so we didn't want to hold up pod a container start time until all of the shared pool containers have been updated, which is what happens whenever one of these pods lands.
Yeah,
and a core is allocated to it, and then every container in the shared pool on the system has to be updated, which is, could be on the order of hundreds.
And I think
so
what we talked through on that, I thought, was that for folks who are particularly sensitive to that, like we could have in the downward API a field that let you know if everyone else was off it yet, and then you could gate a readiness check against that, correct?
Why do we have to update every container? Can this be at the quas C group level? Like you're basically trying to control what CPUs.
Well, I think right now Vishy has to do it at the container level because it sounds like Docker was passing all allowed CPUs, if not masked. If we can get that bug fixed or we can iron out that detail, maybe we can only do it at a higher level, but then you still have to do it at the container level if you wanted to let a sidecar container not run on the shared pool.
Yeah, and the CPU set controller doesn't work like that. So if you have a child who's got CPUs 0 through 3 set, and then you try to go to the parent and confine to 1 to 3, that won't work because it's got a child that it doesn't propagate the confinement down.
So are you trying to say that CPU set is not hierarchical?
No, it is, but you have to do it in order. So you have to grow them from the top down, and you have to shrink them from the bottom up.
Okay.
Otherwise, the write just fails.
Okay.
Anyway, I think all these good things came out of trying to do the POC, so I think it's been really valuable.
Yeah, totally.
Quick question, Ramki. So, how do you differentiate between the hyper-threading enabled and disabled case?
I just, there's ways of doing it. That was kind of details, and so I didn't implement that in the POC. But you can look at cores, siblings, and proc CPU info, and see if siblings and cores match. If siblings is twice cores, then you can assume hyperthreading is enabled.
Okay, so basically it's part of the plan. Perfect.
Yes.
Okay.
So I think we're up on the hour. Good that we had full agendas. In the interest of giving people their time, and I know they want to get Q17 done, I want to end the meeting now if that's okay, and adjourn to next week. And if folks want to add additional topics for next week other than the follow-up on the device plugin proposal, feel free. And I will get this recording uploaded this afternoon. But any other last words that people want to have? All right. Well, thanks everyone, and good luck getting all our Cube 1.7 bugs down. So talk to you guys later.
Thank you.
Later.